Welcome to today's class on calculus for ML. So this is the first lecture in the mathematics for data science module. So in this module, we'll be discussing all the relevant topics that will be required for your understanding of machine learning algorithms. So we'll start with calculus and then we'll move on to linear algebra in the next few classes, and then we'll move on to probability and statistics. So um, so let's start straight away. So so today we'll talk about some of the machine learning use cases of calculus, and then we'll revisit some of the high school concepts of derivatives, chain rule, and definite integrals. And of course, we'll include some of the concepts of maxima and minima, which will be under derivatives itself. So these topics, most of you who have a mathematical background or have studied well in your high school would be familiar with these concepts. But even if you know nothing about calculus, do not need to worry, because this lecture will cover more or less all the things that are required for studying ML. And it's as you know, in data science there are some topics like neural networks, which and gradient descent, right? So these concepts are well understood if you know some of these concepts. But if you even if you do not know even a bit of calculus, it's not going to impact it your understanding in any way. But you'll get more feel if you go through the calculus topics, right? So yeah, so that being said, let's start with the machine learning use cases. So calculus is widely used for numerical optimization. So of course you have done a lot of calculations on calculating derivatives, integrals, definite integrals, and all of that on pen and paper, wherein you solve it analytically. But for a computer to solve a calculus problem or a definite integral problem or a differentiation problem, so to calculate derivatives, so the computer uses some of the numerical techniques to come up with the numbers. So uh, knowledge of calculus helps in understanding all the concepts like Newton Raphson and all of that, right? So of course those concepts are will not touch probably in machine learning algorithms, but if let's say you in future go into numerical computing and uh, such studies, it will be helpful for you, right? So of course gradient computations, you need calculus, and of course the probability density functions that we'll be studying in this module uh, in the statistics part. So we will be using concepts of definite integrals, right? And the fourth topic, variational inference and related techniques, which is not required and is out of scope of this program, but this is related to Bayesian methods and optimization. So yeah, so these are some of the use cases in ML and advanced ML which incorporate calculus. Okay, so first we'll dive deep into derivatives. So so as you all understand, right? So a derivative is nothing but rate of change. Okay, so it can be looked at in two ways. Of course, physically, if you all look at it, you all know the concept of distance and speed. So speed is nothing but distance covered per unit time, right? So how much distance are you covering in a unit amount of time, be it 1 hour, 1 minute or so. But when you talk about instantaneous rate of change, right? So when you divide the total distance by the total time, you get the average speed, right? So let's say you moved from point A to point B, distance is 1 kilometer, and you took, let's say, 1 hour. So uh, your average speed is basically 1 kilometer per hour. But let's say some point in between A and B, right? So if I pick one particular instance of time, or one particular instance of X, or the distance as measured from point A, uh, at that point, if I ask what is the speed, right? So the it's very unlikely that the speed will be uniform throughout the distance. So if you talk about instantaneous speed, now that is some concept which, for that we use calculus, and these use of derivatives comes into picture in that, wherein you say that, let's say I take a very very so if I say distance is x and time is t. So let's say I take very very small time, delta t, and the distance that I cover in that very small time delta t is, let's say, delta x. Okay, so in that case, delta x by delta t, which is kind of your average speed for that particular instant, right? So if you just keep in mind this quantity delta x by delta t, and now if I say that if delta t somehow tends to zero, what will this quantity lead to, right? So this is where the concept of calculus and derivatives come in. So that is where we say that this is the instantaneous rate of change, which we denote as the derivative. Okay, so we'll come into the equations. So geometrically speaking, if you plot x versus y or y versus x, so change in y by change in x is known as the slope, right? For any particular point. Okay, so what is the change in y divided by what is the change in x, so that is denoted by slope. And this slope is basically what is known as the derivative for any curve, right? So we'll go into the details. So yeah, this is the mathematical formula. So the derivative of function y equal to fx with respect to x is defined as this. So what is this? Let's try to understand, right? So I gave you the example of distance and time. So let's say there are two variables. There is one variable x and y is a function of x, right? So if you, let's say, change x by a delta amount, right? So let's say delta x is the change in the value of x. Then what will be the corresponding value of y? So y will become f of x plus delta x. Okay. So if you want to calculate delta y, what will be that? So delta y is nothing but f of x plus delta x, because you have increased x and this is the value at increased x that you are subtracting with the old value of fx, right? So if you take the difference, this is what is the change in y, because y is nothing but fx. Okay, so if I write it in this form, right, so delta y by delta x, and then I say that if somehow, let's say, delta x tends to 0, okay, then what will be this quantity, right? Then this quantity is known as the derivative of the function. Okay, and this will hold only when this type of limit exists, right? So we will not go deep into limits, but yeah, so this is the formal definition of derivative. So a lot of ways to denote a derivative. So for y equal to fx, if you are taking the derivative with respect to x, it can be represented as dy by dx or f dash x. Okay, so this is how we can denote it. And so uh, so before going into the chain rule, I just want to see if you are comfortable with this stuff. So let's I'll share a link of Padlet with you. So please open this link that I provided in chat. So I just want to know, let's say, let me devise a question for you to understand how much you have got. Uh, so let me just write a random function. So let's say x square. Okay. So if or let's say 3x. Okay. So let's say if so this is my fx, right? So let's say if I change x by, what will be the corresponding change in? So do this calculation. So first put the old value of x, which is nothing but x, let's say. Let's start with initially x is equal to 3, or let's say 5. Okay, so initially x is 5. Okay, so your y is basically then 15. Okay, if you change x by 0.0001, what will be the corresponding change in the value of y? What will be the new value of y, let's say? Are you guys able to write? Okay. Uh, okay. So your new value of y becomes 15.003. So what is the corresponding change in y? So initially it was 15. What is your change in y? So change in y is 0.003. Right? So then what is your delta y by delta x? Okay. So what is that value? Start writing. So what is your delta y by delta x? So the change in y you found out, the change in x is this. If you divide, what number you will get? Okay, delta y by delta x is 3. Okay, yeah, so it is that simple, right? So uh, so you are essentially finding out the what is the change in y if you slightly change x, right? And this is all that you need to know for gradient descent, at least when you study neural networks, right? So if you are changing x by this much amount, by how much amount will y change? Okay, so yeah, I think you got this particular concept. And when, let's say, you have multiple variables, okay, you will use what is called as the uh, you will use some composite formulas, but the essence remains the same. Let's say there are a lot of variables on which y is dependent. Let's say y is a function of x and z. Okay, so then the question will be, if you change x by a certain amount, what will the change in y, given that the other variables are constant, given that z is constant, right? So this is how we'll see we will look at the derivative part. Okay, so let's move on to the next concept, which is chain rule. So in chain rule, what happens is that you try to So you have a composite function. So the function is not a simple one, right? So it's of course the function is of a single variable, but it's a composite one. So let's say you have y equal to x, which is a simple function, right? But let's say composite function will be something like y is equal to sine of 3x. Okay, so wherein um, if you can consider sin x as a separate function, here you are here your sin 3x is nothing but a function of a function. Okay, so what I mean by composite functions is, let's say y is equal to sine of 3x. Okay, here I can write 3x as one function and sin x as another function. So let me just do that. Okay, so let's say I define gx as sin x. Okay, and then let's say hx is your 3x. Okay, so I define, let's say, a function which is it's a function of x, but let's say I define it in such a way. So here, what can you just write in chat? What will be the function value? So first you have to see what is hx. Hx is nothing but 3x, right? So this is nothing but g of 3x. So g of x is sin x. So g of 3x will be sin 3x. Okay. So this is your y. So this is why this y is a composite function, because you can express it as a function of function, right? Now let's say you can have another construct. Okay, you can have y is equal to, let's say it's a different function, let's say a of x, and this is nothing but, let's say, h of g of x. So what is the formula here? What is, or what will be the function of x? Okay, so here h of gx is what? Sin x. So, and hx is what? 3x, right? Hx is nothing but 3x, so it will be 3 sin x. Okay, so now how do you calculate the derivative of these functions, right? So uh, of course you some of you might remember you have standard formulas for derivative of standard functions, right? So for example, x to the power n, you have certain formula, right? For sin x, cos x. So all of these standard functions, you have certain formulas, right? But no one will explicitly mention the formula of sin 3x, so that you have to calculate. So this is where we study the chain rule. So what this says is that, let's say if you have a function which is of this form, let's say, now you want to calculate the derivative of fx. Okay, so what you do is, first you take the derivative of g with respect to hx. Okay, so this is quite simple because you take this as a whole. Okay, so and then you take the derivative of hx with respect to x. So you can also view it as, this and this cancels out. This is this and this cancels out, right? So you can view it as at this way, right? So these two cancels out. You can just this is not the correct way or the mathematical way to interpret, but to remember, you can just view it that way. That, essentially you want to find out dg of hx by dx, but you are introducing these two elements because there is another hx in between, right? It will be more clear if I provide you the formula or example. So let's take this example. So you need to let's say find out the derivative of sine 3x. So here you can see that this is a composite function. So sine of x can be treated as gx, and 3x is nothing but hx. So what you will do is you'll use this. So first I will find out the derivative of sine 3x with respect to 3x. Okay, so with respect to hx first, right? And then you will find out the derivative of 3x with respect to x. Okay, so how to find this out? So all of you, most of you know that the derivative of sin x is cos x. Okay, so what you will do here is that you will take the derivative of this, right? So you can treat 3x and this 3x as some single variable. You can take it anything, right? Because these two are same. Okay, so uh, so this is essentially nothing but uh, d by dx of sin x, right? Which will be nothing but cos x, but since the your variable is 3x, you will take 3x. Okay, and then this is quite simple. So derivative of 3x is 3. Okay, so this is how you calculate derivatives using chain rule. Okay, is it clear now, Sirish? Okay, okay, so let's move to the next topic, which is minima and maxima. Okay, so in minima and maxima, so how do you find the minima and maxima of different functions, right? So this is the problem that you will see, right? So let's say this is a function fx, which is denoted by this blue line. Okay, So in a smoothly changing function, so when I say smoothly changing, uh, it's like uh, a function which is kind of continuous, right? So in such kind of functions, a maximum or minimum is always where the function flattens out. Okay, as in when it becomes parallel to the x-axis, right? So if you notice in this curve, um, you see that the maximums of these curves occur at points wherein it goes and flattens out, right? So it becomes uh, almost parallel to the x-axis for some instant, for some amount of time or space, right? And this is true for minimums as well. So whenever a function attains its minimum value at some in some range, it kind of flattens out, right? So it kind of becomes parallel to the x-axis at that instant. Okay, so this is where I would like to introduce the concept of local maximum and local minimum, right? So every function has uh, uh, let's say a global optima or a global minima or maxima, wherein the function takes its highest value, right? Overall in the entire domain that it is existing, right? But what is local maximum, local minima then? So every curve has its ups and downs, right? So there may be a lot many local maximums and local minimums in a particular function, but global maximum and global minimum only can only be one, right? And then you can say that not every function will have a, let's say, a global maxima, right? So if you consider a u-shaped parabola, in that case you will always have a global minima and not a global maxima, right? So yeah, so every function has its own ups and downs. Every curve has its ups and downs. So each of these ups and downs can be called as local maximums or local minimums, because as compared to the points in the vicinity of the local maximum, that point has the maximum value. So if you take this point and compare with the points in the vicinity or in the neighborhood, you will see that this point is taking at this point the function is taking the maximum value as compared to its neighboring points. I'm not saying it is the global maximum, because maybe there is some other zone or some other range wherein that ultimate peak is being observed, right? But there can be many local maximums, okay, wherein at that point, if you compare the values of that point with the neighborhood, you will see that it is beating the others. Similar notion or definition can be given for local minimum, wherein at a point where there is a local minimum, if you compare the values uh, in the neighborhood of that point, you will see that the values of y or fx are higher than the local minimum. Okay, so and of course this point is very important. So the function flattens out, right? So what do we know uh, about such points? So for such points wherein the function flattens out, we know that the slope becomes zero, right? So when the slope becomes zero, what can you say about it? So it's essentially meaning that your derivative or dy by dx at that particular point has become zero, because at this particular point, if you consider the change in y with respect to the change in x, it's kind of not changing, right? So the delta y becomes zero even if you change x slightly at this particular point, right? So every continuous function will have yeah, so basically, yeah. So of course, functions like let's say you have y is equal to 2, which is a constant function, right? In this case, you can hardly come up with a concept of local minima, local maxima, so on. So it's not important to have all of these, but in general, you should try to remember what these mean, right? What does local maxima, local minima mean? Okay. There is another concept which very important in terms of interviews, and it's asked when you it will be required when you study deep learning, which is the concept of saddle point. Okay, so there are some points wherein the derivative kind of becomes zero, but it is neither the local maxima nor the local minima. Okay, so these are such points wherein you can see that the curve comes in such a way, and then it flattens out, and then it starts dipping again, right? So it flattens out for a small instance, but these points you will not watch, never watch a local minima or local maxima. So these points are what is called as saddle points. So whenever someone wants you to define saddle point, so you can say that the points where the derivative becomes zero, but it is neither a local minima nor the local maxima, then that point is called saddle point. Okay. So in this example, if you consider, if this is the range or the domain of x in this particular example, you can say that this is the local maximum, but this is the global maximum, because this is the maximum value that this function can take in between this range, right? So whatever is visible to us in this, if this is the entire domain of the function, let's say this value is -1, this is, let's say, +10, right? So from -1 to +10, if this is the only domain of this function fx, you can say that this point is the global maximum, right? Whereas this point is the local maximum, right? Of course, both of these are their local maximum, because in this locality, this is the maximum value, right? In this locality, this is the maximum value. So in a local region, if it is showing a maximum or a minimum characteristic, it is of course a local maximum and local minimum. But let's say if you see the overall plot of this function, right? And if you find that whichever point at whichever point the function takes its maximum value, you can call it as global maximum, because globally in the entire domain, that point is the highest. Similar logic is for global minima. So in the entire domain of the function, if the value taken by the function is the lowest at that particular point, so that point is called as the point of global minimum. Okay. Yes. So essentially, the if you take the maximum of all the local maximums, it will result in the global maximum, right? So let's say if this value is 2, if this value is 3, you take the max of 2 and 3, it becomes 3. So 3 is the point of global maximum. Okay. So where does it flatten out? Where does the curve flatten out? Of course, where the slope is 0, right? Where is the slope 0? The first derivative will tell us, right? So you just have to differentiate the function and equate it to 0, right? So dy by dx equal to 0. You solve this equation, you will get some values of x. At those values of x, your you know your function will have a local maxima, local minima, or a saddle point. Okay, so how do you differentiate which is maxima, which is minima, when you are dealing with just functions and you are not able to see the plots? So in that case, you will have to take the second derivative, right? So whatever derivative you got, you have to differentiate it again, right? So how do you know if it is maximum or minimum? So that second derivative will tell us. Okay, so if the the so here you get two values, x naught and x1, let's say, of x. Right now you want to find out, let's say, which of these is local maxima or minima. So let's say I consider this point x equal to x naught. So we are trying to analyze where whether x equal to x naught is a global maxima or global minima, right? So what you will do, so at x equal to x naught, you will calculate the second derivative. If that value comes to be less than 0, then x naught is the point of maxima. Just remember, if it is less than 0, then it is the point of maxima. If the second derivative's value is greater than 0, then x naught is the point of minima. Okay, so let's take an example of this to illustrate. Okay, so let's take any function, right? So let's say y is equal to, can you quickly give me what is the if you just break this down and get it into a polynomial form, what will be the value, what will the function? So I just want it to be in terms of, so can you write what will be this? Guys, take a pen and a paper for today's class, because you will be needing that in the quiz as well. Can you verify if this is correct? Okay, so let's move on to finding the where the global minima and global maxima lie for this curve. Okay, so let's say we need to, of course, find out the first derivative of this, right? So f dash x is nothing but 3x square. So this is x to the power n. The derivative of that is n x to the power n minus 1. And then similarly, if you do, it will come out to this. So the next step is you equate it to 0 to find out which are those points wherein the curve flattens out, right? So you'll set f dash x equal to 0. This will give you some values of x for which the curve kind of flattens out, right? Can you give me the values of x? Okay, so I got two values of x from this. So then this says that uh, at x equal to 8 and at x equal to -2, you have your curve flattening out, right? So this is what this suggests. So now we will see for x equal to 8, what is the scenario and what is happening in x equal to 8 and what is happening in x equal to -2. We'll try to see that. So now whether x equal to 8 is a global maxima, global minima or saddle point, we'll see that. Okay, so let's calculate the second derivative. So the second derivative is nothing but you have to differentiate this again. So this will be 6x minus 12. Okay, so this is the second derivative. Now you have to find out the value of this second derivative at x equal to 8. Okay, are these values correct? Guys, can you check? Someone says that this is not correct. I just wrote what Krishna said. Can you give me the exact values? Can you give me the correct values of this? Okay, okay. So around 1.42 and 2.57. Okay, this is how this is what uh it is coming, right? So let me just, so we will check for these values, right? So what is the value of uh, the double derivative at these points, right? So let's try it out. So at x equal to 1.42, 6 into 1.42 minus 12. Uh, this is f double dash 1.42. Is this value positive or negative? So is this value positive or negative? So if this value was 2, it would have been 0 because it is less than 2. This has to be negative. Similarly, if this was 2, it would have been 0. But since this is 2.57, this has to be positive. Okay. So then if this is positive, so can you tell me whether this is local maxima or local minima? And similarly, what about this? So this is local maxima because this is negative, right? And this is local minima because this is positive. So the second derivative is positive, and that's why this is the point of local minima. And of course, the second derivative at 1.42, it's negative. That's why this is the point of local maxima. Okay. So this is how you calculate whether a particular point is a saddle point or a local minima or a local maxima. Okay. Anyone has any doubts in this part? Okay. So at saddle points, your double derivative will become 0, right? negative local maxima, positive local minimum, and then saddle point it will become 0. Okay, great. So let's move on to the next topic. Okay, which is partial derivative. So now let's yeah. So in partial derivatives, basically till now what you have seen is functions in one variable, right? So y was only a function of x. um, in chain rule we saw how we can deal with composite functions, but still it was a function in one variable. Okay, so what happens when a particular value is dependent on a lot of variables, right? And this is typically what you will see in or deep learning or machine learning algorithms, right? So of course your y will be dependent on a lot of variables. Okay, so in those cases you can you can take let's say you want to calculate the partial derivative. So what does this mean? So let's say you have a function z is equal to f of x comma y. So z the value of z is dependent on two variables x and y. Okay, so if you change even one of them, the value of z will change. If you change x, z will change. If you change y, z will change. If you change both, z will change, right? So uh, now how do you find out the dependency of one variable on the final output, right? So let's say z is your final output. What happens when I change x by a delta, right? How will z get affected? What happens when I change y by a delta amount? How will z get affected, right? What will the corresponding change in the value of z? Okay, so for answering these type of questions, what we do is that we try to make the problem simpler. We say that when I'm changing x, let's say, I'll not change y. Okay, I'll keep that constant at the same value what it is now. So when I'm changing x, I'll just change x and note the corresponding change in the values of z, right? and and when you find out this part, this is what is known as the partial derivative. Partial because it's not the complete derivative, because you are not taking all the variables into consideration, you're just taking one. So that's why the name partial. So this is why so how do you deal with partial derivatives? So how do you deal with partial derivatives? So uh, you basically change one particular variable, keep the other constant. This is how you get partial derivatives. The formula will remain the same for uh, one variable. You just have to treat all the other variables for which you are not taking the partial derivative as constant. Okay. So we'll move on to example, and then the notations and the concept will be more clear. Okay. So here, let's say you have a function which is dependent on x and y. Okay, so it's 2x square plus 3x plus 6x plus 7y. Okay, so now you want to calculate, let's say, the derivative of uh, this function with respect to x. So you'll not change y. You will treat y as a constant, and then you will take the derivative. So you're changing x, so the derivative of this will be 4x. In this part, you will take 3y as a constant and you will take it out. So the remaining part is x. Only this part will, for this part only will calculate the derivative. So derivative of x is 1. So essentially you are left with 3y. So that's why 3 of y, right? And this part is totally constant. And for the derivative of this part is just 6. So 4x plus 3y plus 6 plus 0. Okay, so this part is entirely constant if you are taking the partial derivative with respect to x. Note that the notation is not d. So In case of uh, derivatives in one variable, we used to write small d, but here just note the change in notation. Okay. So now if you want to calculate the double derivative of the double derivative of f with respect to x, then you need to again treat y as constant, take the derivative with respect to x only. So the derivative of 4x is 4, this is constant, this is constant, so this is just 4. So the derivative of this function with respect to x is 4, double derivative, sorry, right? Now what happens if so this is all good till you are finding the derivative with respect to x. Now let's say someone told you to calculate the derivative with respect to y. So you will essentially calculate the partial derivative. So the in the partial derivative part, you will treat uh, x as a constant when you are differentiating with respect to y, right? So you'll keep x as a constant. So this is a constant, right? So it will get removed. In this part, if you take x as a constant and y as a variable, so 3x will be this part's derivative with respect to y. Okay, so that is why 3x. This part is again only dependent on x, which is constant, so you'll remove this part. The derivative of this part will be 0, and the derivative of this part is just 7. Okay, so with respect to y, if you calculate the second derivative of this function with respect to y, so you will essentially take the partial derivative of this again. So the partial derivative, so this function is again a function of x totally. So the entire derivative will be 0 if you differentiate with respect to y, because x is a constant, variable y is not present. Okay. Similarly, there is one more construct. So first you, let's say you want to differentiate with respect to x, and then you want to differentiate with respect to y. So then what happens? So essentially, if you want to take the derivative of this part with respect to y in the second time, right? So del f by del x, and then you take the derivative again with respect to y. You took once the derivative with respect to x, now you are taking the derivative of that with respect to y. So then you will treat x as a constant now, right? So the derivative will essentially become, so this part will become 0, this part will become 0, you will remain with 3, right? So this is one of the important properties wherein either you first take the derivative with respect to x and then you take the derivative with respect to y, or you change the order. So let's say you take the derivative with respect to y first and then with respect to x, both of them will give you the same value. Okay, so this is another one of the properties. Okay, so now so I hope the partial derivative part is clear. Okay, if anyone has any questions in the partial derivative part. Okay, great. So so the next topic is slightly complex, but this is something which you need to remember, because this is what will be used in calculus. In deep learning when you study gradient descent, even in machine learning algorithms when you study gradient descent. So this is nothing but an aggregation of all the derivatives of a particular function matrix, right? So you were taking just one function till now. Now let's say if you have a lot of functions, right? So you want to take the derivatives with same set of variables. So how do you represent it, right? So don't get intimidated by this. I'll explain how do you remember this Jacobian matrix. So yeah, so let's say you have a function, right, which is a two-dimensional vector, right? So you have So this is a kind of a vector, which is a column vector, and each of these elements contain functions which are variables of, which are functions of x and y, right? So the first function is x square y. Second function is fx plus sine y, right? So two functions are there. Now, so this I can represent as f1. This I can represent as f2. Okay, so essentially you have a column vector with two functions, okay, f1 and f2. Okay, so what is Jacobian matrix of this vector? So it's nothing but you take all sort of possible combinations of the derivatives and store it properly in a matrix. That's all. So first you take the derivative with respect to x, okay, of f1, and you store it in the first element. Second, you take the derivative of the same function with respect to y and store it. Okay. Then what do? You take the second function, take the derivative with respect to x first and place it here. Then you take the derivative with respect to y and place it here. So basically, let's say if you have the generic scenario wherein, let's say, um, you have, let's say, n number of functions and n number of variables in each of the functions, right? So x1, x2, x3 till xn, and f1, f2, f3 till fn. So here what is happening? So this was f1. So for f1, whatever derivatives you calculate with respect to x, y, or x1, x2, x3, xn, you store it horizontally in the first layer, right? So in the first row. So f1 and all of its partial derivatives with all of its variables are stored in the first row. Similarly, for the second row, f2 is there. So you store all the derivatives of the second row, all the derivatives of partial derivatives of f2 in the second row, right? So this is what it has done. So you can now calculate the derivatives. F1 with respect to x, partial derivative of x1, f1 with respect to x comes out to be 2xy. So take y as constant and then 2x is the derivative with respect to x, and so on. So if you calculate for all the four, you will get this matrix. So this is what is known as the Jacobian matrix, right? So fancy term, but it's pretty simple to remember. So you have a column matrix with whole lot of, let's say, functions of certain variables. Now you want to take the derivatives. Of course, there are Jacobian metrics for 2 cross 2 and all of that, but you do not need to uh, remember those. So just you can just focus on this part. Okay. So the use of Jacobian right now, no, I do not want to mention. You will encounter this when you study machine learning algorithms and the optimization algorithms like gradient descent and others. Okay, so just remember this concept. What is a Jacobian matrix for now? Okay, and how it is calculated. What is essentially a Jacobian matrix and how it is structured. That's all you need to remember from this class. Okay, so you can structure it in this manner. Okay, uh, each function will have different same number of variables or can be different here. So for now, let's consider it has the same number of variables and the same number of functions for simplicity. Okay, it can have a different number of functions, but yeah, so you can essentially generalize if and when required. Okay, but for now, for simplicity, let's take it that way. Okay, so so there is one more concept, which is the Jacobian determinant, which is nothing but if you can find out the Jacobian matrix, you can also find out the Jacobian determinant. So it's nothing but the so you just multiply these two and take the difference with the product of these two, right? So this is what is the Jacobian determinant. You will learn how to calculate determinant in the linear algebra classes. Okay, so essentially, yeah. So if I have to, let's say, make a comment on that, because determinant is only calculated on square matrices. So you can assume that number of functions and the number of variables on which those functions are built are the same. Only then we can have these kind of constructs. Okay, great. So I hope Jacobian matrix construct is clear. How do you form it? So f1 f1 and then x1 x2 f2 f2 x1 x2. Okay, great. So yeah, so I know many of you have forgotten some of the calculus formulas, but if you remember these, it will be uh, helpful for you in calculating the derivatives if and when required. So you can just revisit these formulas. I have put it in a slide, right? So the derivative of constant is 0. The derivative of x to the power n is nx to the power nx to the power n minus 1. And where is ln x? So derivative of ln x is 1 by x. I'll give you 1 minute to revisit these formulas once, because you might need these in the quiz. So just glance through the formulas and try to recap whatever you had learned. You'll be needing this in the quiz. Okay, I hope you have gone through that these formulas. So let's move on to the last topic for today, and post that we'll do some experiments on calculus in our data science lab. Okay, so yeah, so the last topic that I want to discuss for today is definite integrals, and this concept will be used in your study of probability density functions. Okay, which we will cover later in this module. Okay, so the integral of fx corresponds to the computation of the area under the graph of fx. Okay, so this is the definition of definite integral. So it corresponds to the area under the curve. Okay, so it is denoted by two limits. Okay, so you write the lower limit here, the upper limit here, and then you write the function, and then you write the derivative with respect to the variable with respect to which you are integrating. So just remember, integration is the opposite of uh, derivation. Or uh, so if you, let's say that the derivative of fx is f dash x, then the integral of f dash x is fx. So it's exactly the opposite or the inverse. Okay, so similar to the formulas that I gave you for derivatives, there are formulas for integrals as well. Not required much. If you want, you can go through them, find them on internet and go through them, but not required. Okay, so yeah. So for any function, if you write this construct, what this means is that what is the area covered by the uh, curve fx between x equal to a, this line, x equal to b, x axis, and the curve. Okay, so this construct basically means what is the area enclosed under x equal to a, this is that line, x equal to b, right, this is that line, two boundaries, x axis another boundary, and the curve. Okay, so this is what this notation means. Okay, okay, great. So So now let's uh, move on and see some of the experiments in Desmos and GeoGebra. So these concepts will, you'll be able to relate more. Okay. So let's go one by one. So the first experiment that we'll be doing today and trying to visualize how uh, tangents and derivatives actually look like in graphs, right? So let's say I have a function, right? I have a function which is denoted by sin x plus 0.3x. Okay, so this is your function and this is denoted by the blue line. Okay, so this is the blue line uh, which is your denotes the function. Okay, now let's say you want to see how the derivative is changing with x. Okay, right? Uh, so here is a slider that is provided, so you can just vary the value of a, right? A is nothing but no, this value, right? X. Okay, so if you change the value of x, how is your how is the value of your derivative changing? Okay, so if you just start moving this slider, you'll see that the red line is changing, which is basically denoting the slope at that particular point, right? And it is basically denoting the tangent, right? So when the tangent becomes exactly parallel to the x-axis at this point, let's say, when it becomes exactly parallel to x-axis, at that point you will notice a global minima or a global maxima, right? Which is the case in this case. At around minus 4.4, it has a global it has a local maxima, right? So you can see this, right? So again, if you go here, um, so at the point where the line becomes parallel to x-axis, that means your slope becomes zero. It there is a local minima or a local maxima there. Okay, so you can see this, or of course a saddle point, right? So this the tangent line will again become parallel to the x-axis in points where there is a saddle point as well, right? So you can just play around with this and see how the curve is changing with the value of x. And you can notice that when the line is making a acute angle with the x-axis, at those points the slope is positive, right? So in this case the slope is positive, right? But let's say in this case wherein it is making an obtuse angle with the x-axis, this tangent line, the slope is negative. Okay, so slope is nothing but the angle made by the tangent of the angle made by the slope, right? So what is the angle this substance with the x-axis? So this is what is the slope. So basically tan theta, right? So if you visualize, this is the uh, angle subtended by the slope at this point. So if you want to calculate the slope at this point, it will be nothing but tan theta. Okay. So similarly, you can change the functions here, and you can, so when you, let's say, encounter sigmoid functions or ReLU functions in let's say when you are studying deep learning, you can come back and use Desmos to visualize how the derivative is changing with the value of x, right? So let's take some more examples. Right? So okay, so let's say this is your function. Okay, this is the sigmoid function, right? You will encounter this in deep learning very often. So let's say what happens when what happens to the slope for this function. So if you see the properties of this function, this lies between 0 and 1, right? This function lies between 0 and 1 only, and you can see the whole function lies between 0 and 1, right? So it takes a value of zero point 0.5 at x equal to 0. Okay? At x equal to 0, it takes a value of zero point 0.5. Okay? And it's like a symmetric function with respect to the y-axis. So and yeah, so for very high values of x or very low values of x, it kind of saturates. So for very high values of x, this becomes 1, right? The value becomes 1, it saturates at 1. You can see that. So around, let's say 4.5, it has almost reached the value of 1, and beyond that it has almost reached 1. But actually it will never take the value of 1, because for that you need x to be infinity. Okay, similar thing you can observe here on the negative side. So for very large negative values of x, the function takes a value of 0 and it saturates at 0, right? And it tends to 0 when x tends to infinity. Okay, so if I want to watch the derivative, how this varies for this function, you can see that for very low values of x, the derivative becomes very small, as in it becomes parallel to the x-axis for low values of x, and then it increases gradually increases till x equal to 0, and then it starts decreasing again. Okay, and then again it becomes 0 at for very large values of x. So this is the one property of sigmoid function which you need to remember. So the derivative becomes 0, is 0 for very low values of x, then it gradually increases, and then the derivative becomes 0 again. So yeah, so this is one of the properties of sigmoid functions. For very large values of large positive and large negative values of x, the gradient or the derivative is almost equal to 0 for the sigmoid function. Okay, and later when you learn deep learning, there is a very typical problem in deep learning called vanishing gradients, and that is why we do not use sigmoid as the activation function in your neural network layers. And this concept, if you could not get the last two lines, it's totally fine. This you will learn later in deep learning, and that is why, to set context of the sigmoid function, I showed you this property. Okay, that the derivative kind of becomes 0 for very large and very small values of x in case of sigmoid function. Okay, this is the sigmoid function. Okay, now let's move on to a different experiment. So, okay, so we can do some experiments on integrals and area under the curve as well, right? So we'll try to just look at the definition and try to see if it holds. Okay, so here, so I have defined a function x square minus 1, and this is the The red curve is the graph, and so let's say you want to take the integral from any 2 points A and B, right? So now we'll try to vary A and B and see how the area is changing. Okay. So let's say I want to calculate the area between -1 to 1. Okay. So area between -1 to 1. So this value is coming up to be -1.33. Okay. So what does this suggest? This is showing a negative value, but you know that area cannot be negative. So why is that so? Can you write in chat? So if I integrate between -1 to 1, this function, right, it is coming out to be -1.33, right? So this area is coming out to be -1.33. Why is this negative? Okay. Yeah, so you have got it correct. So it is because the area lies below the x-axis. So whatever lies below the x-axis will take that area as negative. Whatever lies above the x-axis will take that as positive, right? And that is why, let's say if you start increasing and start taking the area uh, above x-axis, let's say I integrate it from -1 to 2. Okay, now you can see that the value of the derivative is 0. What does this mean? That the negative area and the positive area are kind of equal. Okay, so that is why if you integrate this function from -1 to 2, your total area under the curve becomes 0, which is not the case if you take into consideration the actual area. But by by the notation that we take, no uh, areas below the x-axis will be considered as negative. When added with areas above the x-axis, it kind of neutralizes and pushes it to 0. Okay, so you can use this particular tool, this particular experiment to visualize and maybe come up with values of certain definite functions. Okay, you can use this as a calculator as well. So yeah, so let's move on to a different experiment wherein we'll see how we can uh, see this. Okay. Okay, so let's say I have any function, right? So I need to calculate the area under that curve. Okay, so let's say I have this function gx, which is ln x plus 5 plus 4. Okay, now I want to take I want to calculate the area between a equal to -4 to b equal to 4. So -4 to 4, I want to calculate this area. Okay, now what I have done is that it's very easy for us to calculate areas of rectangles. So we can divide this entire area into rectangles, right? And then we'll try to calculate the values of the areas. This we can do from the graph. Of course, we are leaving out some of the areas, right? So this will give us an approximate value. Okay, so this is what L4 is. It's basically the area um, covered by all the four rectangles. Okay, so it comes around 41.3079. The definite integral, if you go via calculus and calculate it, it will be around 43.775. So the difference in these two areas is because these areas are not covered in this calculation, right? The spaces which are left. So what you can do now to reach the actual value of the area under the curve, can I start increasing the uh, number of rectangles, right? So what this will essentially do is that from, let's say, 4 rectangles, you move to 14, 15, and so on. You see how closer these two values are, becoming, right? So, and let's say if you have infinite number of rectangles, your this value and this value will exactly match. And this is what is the crux of calculus as a whole, right? So you move from a discrete scale to a continuous scale. Okay, so so as you can see, if I take a lot many values of rectangles, this value almost resembles the value that you can get through performing a definite integral, right? And this is the crux of calculus. So when you are studying, let's say, probability distributions, you will be studying two things: discrete and continuous. So all the formulas that you will study in discrete, just have to replace the summations with integrals to convert it into formulas of continuous, right? And this is the whole crux of calculus. So you are moving from a discrete step to a kind of a continuous step. Okay. Okay. So I hope you play around with the experiments and carry out your own experiments as well with different functions, different values.